Hello, I'm Stefan Gruber, I'm project leader for LXD, and in this video, I'm going to be continuing the series on devices, and specifically going to be looking at the LXD TPM device. So for those not familiar, TPM stands for Trusted Platform Module. It's usually an extra chip, or these days effectively software running in a secure part of the CPU that can be used for a variety of cryptographic features. It includes things like hashing and extending a hash of a variety of things during boot, which can be used to get effectively like a validated chain of everything that happened on the system that can then be used to validate whether a system executed the expected firmware, loaded the expected devices, firmware configuration, bootloader settings, bootloader itself, kernel, and everything else on the system. It can also be used with advanced kernel features to even validate every single binary being executed on a system. It can be used as a source of random for the system. So you can see the random number generator using a TPM. It can be used to effectively seal cryptographic keys. So you can generate a key pair that is tied to the TPM, which you can then load, but only so long as the TPM is in a given state. So if your system is somewhat compromised, if the firmware has been changed or something, the TPM won't release the secret that you then need to access the certificate. There's a lot you can do. It can be very complex, but effectively LXD does support TPMs. What's a bit unusual possibly is that LXD supports TPMs not just for virtual machines, but also for containers. And the way we do it in both cases is that we use a software TPM, which is a project called SWTPM. And that provides us with a TPM v2 implementation that we can expose either to a virtual machine or a container. And yeah, for the container case, it's mostly limited to using it to seal certificates. That's the main use case for it, effectively using it as some kind of HSM, so hardware security module, so that you can store keys effectively outside of the container and making it impossible for someone to straight up steal those kind of keys. For virtual machines, it's a bit different. You can still use it for that, but in the case of virtual machine, it also gets all of the hashes of everything that happens during boot, so you can actually use that to validate the virtual machine. And that's what's then used by the likes of Windows BitLocker and similar disk encryption technologies to do full disk encryption in a way, but in a way that doesn't require you to enter a key at every boot, by effectively tying the decryption key to TPM state, so that so long as you're running on the same system, just with the same TPM, your system will just transparently boot and with the disk decrypted. But if anything changes, if you change firmware in a significant way, or if you change some other pieces of the hardware, that will effectively invalidate that state. The TPM won't release the secret, and that then causes one of those recovery prompts you might have seen for full disk encryption. All right, so as you can see, not very much in the way of configurations. One thing that's interesting is that you can technically attach multiple TPMs to a container or a virtual machine. That's not something that's very commonly seen on physical systems. On physical systems, you usually either have a firmware-based TPM or FTPM, or a physical TPM, so like a discrete TPM that's physically connected on a connector on the motherboard. But my understanding is that most firmwares make you pick one or the other and don't enable both of them at once. LXD doesn't really care, so there's no issue with us running multiple TPMs. Now, whether the operating system will necessarily understand what's going on, that's a different matter. All right, so let's go look at the terminal. And here I've got LXD 5.11, but it doesn't really matter because TPM support's been around for quite a while. Trying to remember when it was, like LXD 4.1 or something like that. So we've had it for really quite a while, which was very, very convenient when Microsoft then decided to make TPM effectively required for Windows 11, because LXD VMs then pretty much just worked. You just needed to add a TPM to your VM and off you go. So let's start with a container. So I'm just gonna start in Ubuntu 2204 container here. Let's call that C1. And out of the box, you're not gonna have a TPM in there. So let's just go in the container, install TPM2 tools. And then with the tools, we're just gonna be trying to read all of the registers, which are those kind of hashes that happen during boot. Let's read PCR read, I think is a thing, yeah. So this is failing quite miserably. That makes total sense. There are no TPMs attached right now. Now let's go back and add a TPM to the container. So we do that. We call the device VTPM, virtual TPM. The device type itself is TPM. And then there are two arguments that need to be passed. You'll get an error if you don't. The first one is the path. So let's do TPM0. And the second one is the path for the kernel side node. I believe that's what it is, TPM. Then you add those, go in there, run PCR read again. And what we effectively see is that all of the PCR registers here are all empty, which makes sense. Nothing's ever been measured into them. If we reboot the container, one thing that might be interesting is to see whether systemd or anything during boot uses those registers. I would be kind of surprised if they did for containers, but it's not impossible. So let's just try that again. Now everything is blank. So as I said, not very useful in a container as far as validating the state of the system, but it can still be used to handle secrets and store certificates and that kind of stuff. Most often you're gonna be doing that using a PKCS11 type plugin, which then hooks into the TPM. All right, now let's do a virtual machine. So for a VM, I'm gonna be using 2204 cloud image and start the VM. In the case of a virtual machine, we can't add the TPM at runtime. So the VM is gonna boot, we're gonna be installing the tools, but then we're gonna have to turn it off, add the TPM and turn it back on. You might also get different results depending on what distro you're on. If you're using the LXD snap, our build of the firmware, which is EDK2 or OVMF, so effectively the open reference implementation of EFI, our build is enabled with full TPM2 support. So we do get all of the hashes and everything from the firmware and early boot, but that might not be the case in your particular Linux distribution. All right, so I'm just going to be installing the TPM2 tools in there as well. There we go. And then do the same thing. So I'm going to be doing a PCR read. And this is similarly failing. So now we're just going to stop that one. And for a VM, things are slightly different. You don't need to specify those paths. So you just need to do device is called VTPM in this case, and then device type is TPM. And you're done. Then you can just start the VM back on. VM is gonna be starting. And start a little bit, we should be able to get a shell, there we go. So TPM2 PCR read. And here we can see things are a bit different. So we can see the hashes are actively been set, which means it did actually get fed values at boot time to measure and to extend those registers. So we can see that effectively register 0 through 10 have been used. 11, 12, 13 are still on default value. PCR 14 has been used, and then the rest are again on their default value. Different registers are used for different things. I'm not super familiar with that, other than I keep hearing that PCR 7 matters, and I believe that's the one that kind of does the early boot and bootloader type hashes. So there's a good chance that the value in there has effectively been a number of hashes for early boot firmware and bootloader and some of that stuff. What could be interesting, I've not actually tried it, but we could just write that down to a file, then reboot the system and look at the difference between two boots. In theory, anything that's kind of boot related, firmware related should not have changed. 2 boots in a row should give us the same thing. But any measurement that's dependent on anything that's kind of user space or time based might be different. So let's just see, we'll do old and new, and then do a diff between the two and see what that looks like. Apparently it's perfectly identical. So that's that's good. All new. Yep. One thing we could try, again, I'm not exactly sure of exactly what gets measured and how exactly. Different kernel would probably do the trick. I don't know if a simple modification to the grub config would be enough. It kind of depends on whether grub is itself is TPM enabled or not, and whether it measures the config or it measures the result of the config. One thing we could try is just powering off the VM. I'm gonna start it back, but this time, and I'm not gonna be able to, actually I should be able to do it from the text console. So let's try and do that. That way you can actually see what's going on. So just gonna be trying to get into the boot menu here. If that doesn't work, I'm gonna have, oops. Okay. So we're in grub. Huh. Okay, I didn't get to stop in the firmware menu as I wanted. So I don't think this will have been enough to trigger a change. Even though I did stop in grub, I did not actually make any change. So let's see. Oh, actually it did cause a change. There we go. So apparently just in this case, stopping in the bootloader and messing around a bit was enough to trigger some changes on register 8 and 9. Not sure exactly what gets measured in there. Again, if it's something you care about, you can definitely go and find a lot more information about how everything gets registered, gets hashed and sent through the TPM, what gets measured by systemd, what gets measured by grub, what gets measured by the firmware itself, and what might be the impact on those values. But here it does show a difference boot to boot, so that's pretty cool. The last thing I wanted to show is kind of the result of that. So here I've got a Windows 11 VM, which similarly has a TPM attached to it. I'm just gonna try and remember where we need to go in there. But if we go into settings, there's like some security panel where we can see that BitLocker and everything is enabled using a TPM. Okay, let's try privacy and security. Windows security. Well, I mean, there's a search. Let's see if the search works if I look for BitLocker specifically. Manage BitLocker. Okay. There we go. BitLocker is on. So that shows that this thing is all enabled, and there's like another link to TPM administration. So that should show us that there's a TPM on the system and it's being used. There we go, TPM management. Yep. So we can see in this case, it shows that there is a TPM. There's a version of the TPM, which is most likely the version of SWTPM in this case. The guy who makes SWTPM, Stefan Berger, works for IBM, so that explains my fictional name here. And it shows the TPM is running a 2.0 version of the TPM standard, and that is ready to use, and everything is all functional. I don't know if they let us do anything else interesting there. Apparently you can clear the TPM. If you do that, that's gonna break BitLocker. So on reboot, it's gonna be asking for your BitLocker recovery key. And that's also how you get to have Windows 11 installed cleanly in LXD. It's that this actually qualifies you for a fully compatible Windows 11 system, effectively. And that's it for TPMs in LXD. That's something that's not super common, probably not extremely used. I think Windows 11 definitely popularized the use of the TPM in LXD because it's effectively a requirement for its installation without having to use workarounds and the like. For containers, it's probably not something that many use, but something that might be interesting if you're handling sensitive cryptographic keys. There is a way to store that data outside of the container. So if the container gets hacked for one reason or another, the hacker would be able to use the key to generate, well, to sign things or decrypt stuff, but it won't be able to actually extract the key itself for its own offline use. So that improves security a fair bit, because as soon as you kick out the hacker, you know that you're like nothing effectively really got stolen, and you can look at the damage and undo it, which is why a lot of the certificate authorities and a lot of more sensitive services like that use HSMs, and a TPM can be turned into a reasonable, cheap HSM effectively. Otherwise, TPM state is stored as part of the instance state, which means if you create snapshots of an instance and you restore the snapshot, the TPM state will be restored as well. I think that just kind of makes sense in general, that this should be considered to be part of the state of the entire instance, but I felt it's something that's still worth pointing out in case anyone's wondering. And that's it for TPM in LXD. So if you've got any questions, you can leave them down below. You can go on our community forum. There's going to be, as usual, the link to the documentation page. As you can see, it's pretty straightforward. For VMs, no configuration whatsoever. For containers, 2 configuration keys to just give it where you want it to show up in /dev. And that's it. Thanks very much. See you in the next one. Bye.